I thought that was fun.
I wasn't too happy. I'll be happy with a solid C on that test. And you know they get harder after this. He was talking to my one of my group members and I in the office saying, yeah, I'm thinking about making one of the later tests like a booklet so long that no one can finish it within the time frame.
What? He's a pretty fun guy.
And he said, because he says that this is what happened at some of the colleges he was at, where that's what they did.
Right.
And he said, whoever finishes the fastest, I'll just give him the best grade.
He's a funny
That's
guy.
horrible.
Well, because he was talking about how like he usually was like the first one done, and he usually was like the one that did the best. And there was like some people that took the full 2 hours, and usually were doing this the hottest.
See, my difficulty professor would do the opposite. So if you turn it in first, like he wrote down the time and turned it in on a free test. And if you turn it in first, he would grade it really high. And
Are
if
you
you were the
serious?
last person to turn it in, then he would be like, "Oh, you ran out of time, so I'll grade it easy." Like no joke. So if I didn't know how to do something, I would literally just sit there until the end of the class. He would like be like, "Oh, you ran out of time. Here's some 3 points."
Oh my god.
Well, I think what Yang was trying to say was usually the people that finish first are usually the ones that actually understood the material the best.
Well, you
Yep.
either understand it or you don't understand it at all, so you don't have anything worked out.
Yeah.
Like one or the other way.
I'm definitely having a test with like 3 blank. I'm like, yeah, here you go.
Oh no, I always write something down, especially for like math ones.
Something else. I haven't
Sometimes, like in the cooking test, I didn't have any worked out. Like you couldn't
Oh,
formulate.
Calc
any-
3 was that bad.
Yeah,
something
I
like
haven't.
that. But if I wait until end of class,
So you just sat there just looking
Oh,
dumbfounded.
like that, but,
Won't make very much.
You want more?
Yeah, please.
So how's your morning? Is it the first class in the day or like
no.
fifth?
Fourth. This is the 4th class for me.
Fourth class from the morning?
Yeah.
Me too. I cannot. No.
Dang.
I actually only have 10-minute breaks in between each one.
No, I cannot.
Impressive.
You're kidding.
On Mondays, I have 2 labs after this class. So
And before you have 3 classes? From
Yeah,
8 to
yeah.
9, from 9 to 10?
yeah, I go from 8 to noon, and then on Mondays I have physics lab, and then I have analytical lab after that on Mondays.
Well,
Fridays are nice. This is my last class.
Mondays is
You-
intermittent.
you have a busy schedule.
Yeah.
Would it be better, well, now we cannot change anything, but would it be better for next generations to have it on like Tuesday and Thursday?
Yeah. My Tuesdays and Thursdays are basically barren.
I like this semester.
Huh?
So I like this semester. I'm good with this.
Yeah, I remember it.
Well, I was trying to push it to Tuesday and Thursday, but there was a conflict because some
Yeah.
other required classes.
Analytical.
Okay, so who we are and what are we doing? Where we are now. I think we are in the physical chemistry class. And we are promising each other, well, I'm promising you that one day we will perform theoretical characterization of materials and molecules, predicting properties and interpreting outcomes of experiments with all power of theories, right? So I'm not diverging from what I was promising a month ago. But instead of doing this, we are going through more and more boring mathematical stuff.
Oh.
So in order to do physical chemistry, you need to do some quantum.
That's right.
But we all are tired of homeworks. Well, I'm probably more tired than you. And here is an experiment to make next homework not pen and paper written, but computerized, because you already are certified experts in scientific computing, so you know how to use MATLAB, and we will. This is a material which is equivalent to like 6 lecture hours, but in with appropriate tools in computer lab, you can cover it in like 40 minutes, and just print screenshots of the images, and I hope you are counting number of questions, but I was trying to extend it with a lot of words. In fact, it is just run the code 4 times, like change number, hit run. Okay, so it is quick. So the questions for the homework are set up. Can you pass it? Are set up in such way so that it covers things that were not yet covered in class. Otherwise, it would be completely boring. It would be backwards. So it's arranged a little bit forwards. So the first question is based on our wish to predict future, right? And we cannot predict future for too many systems. We can predict free electron in the space, and we will be able to predict something for electron enclosed in the box. And the question here is predict the evolution of the position of an electron if it is enclosed in the box and if the initial conditions are prepared in a specific way. We are going to cover it in class on probably Friday and Monday, but at the same time we will cover it in tonight's lab within 20 minutes. So it's super easy, especially if the codes are pre-made. And part 2, it looks forwards towards the next week. A lot of courses are set up in a surprise facility, like something boring. Then, what a surprise! And we find some little feature which should be a big result. I can play open cards here. So next couple of meetings we will deal with predicting future, and then we will think outside of the box. Not in the figural speech, in the literal way. Instead of one-dimensional box, we will look on 2-dimensional, 3-dimensional, and see what happens. So the second part of the homework is related to the multi-dimensional box. And I have big hopes that tonight in the lab we will cover it as well. If you will not, then I will not have a moral right to request this to be done from you guys. Any questions about homework? Of course, one needs to sit, concentrate, and probably I need to retype it in more visible font. But is it clear about general idea? And I have sent you an email with codes. So if you're busy tonight, you can just run it on your laptops and see what happens. I don't know, what we have to do today is something really simple. You can find it in any textbook, and basically it is just 2 equations. So by the end of today's meeting, we need to have the eigen functions and eigen energies of electron in the box, right? And I wouldn't be surprised if I realized that all of you already know this answer. So I will entertain myself by going through steps, how these solutions are coming from. But derivations can be boring. So let's start from analysis, how they look like and what are the benefits. And then maybe some of you need to depart to something more interesting or to the next class. And I will do the boring stuff for the record. So, scientists are masters of the universe. we are not supposed to do boring math. We are doing it from time to time. But math is a servant of a scientist. So I hope there are no professional mathematicians in the audience. Okay, we are majority. You cannot fight with us.
It's okay, I agree anyway.
So, from point of view of scientists, math is just a tool, like an instrument, like a spectrophotometer or whatever, NMR. But we need to set up right questions. And then we are looking in Wikipedia for answering question that has been postulated in the right way. Or we can hire a professional mathematician and solve it for us. We just need the answer and we will analyze it. So if you are looking on a box and we are not yet strong enough to look on time-dependent perspectives, I'm just going to spice our today's meal so that you will be not bored. Because these two equations and their derivations that are coming up in any textbook is boring. But which scientific question can we pose to ourselves while we are solving for boring time-independent Schrödinger equation for a particle in the box? So we may look around on our rich experience in this course, and our rich experience is limited only to electron in free space. So what do we see there? If you look on the eigenstates and eigenenergies, eigenfunctions and eigenenergies, what were the eigenfunctions for electron in free space?
E to the negative phi kx.
I hear the voice of mathematician. Anyone with physics, minor, major, what are the right word for this function?
Plane wave?
Yes, so plane waves, right? Here is what we did, this oscillatory exponential. So this k determines the momentum, determines the velocity. Are there any restrictions for the plane wave? Were there any restrictions for the value of the k? Is it like, were there traffic signs, like you can go with this momentum and you cannot with that? Do you remember anything of this? I don't, maybe you do. No? So any momentum was allowed. So any momentum is eigenstate, plane wave is any momentum is eigenstate of plane wave free electron Hamiltonian. Right? Positive, negative, zero is allowed, was allowed. What was the minimal energy?
Zero.
Yes. So if it is like positive or negative, it is above zero, p squared. If it is zero momentum, then zero energy. So the lowest possible energy was zero. Now, if we are confining our electron, so what we do in the box means that we are trying to describe all oligomers of conjugated polymers and nanostructures, semiconductor nanostructures. Can we say that there the lowest energy will be zero? Can we say that electron can travel with any velocity there? Or maybe there will be traffic signs telling, not this velocity. Just ask yourself, if you have some answer, you can write in your notes or raise your voice. So, we are in a free country. Let's make a voting. Who thinks that electron is allowed to have any momentum in a box? moment. Okay. Who votes that there are limitations for allowed velocities for electron in a box? Okay, Austin?
Still deciding.
Okay, please.
I think I don't know. I don't see why it couldn't, like, why it would have restrictions. I guess.
Good question. Because it is a
Assuming
wave.
that's what we're gonna explain, right?
Because it is a wave.
Right.
And while reflecting from the walls, if it is in the eigenstate, it should, after reflection and coming back to the same point where it started, it should came with the same phase. And this phase should be integer number. Therefore, make sense? So it will be some, but we will come to this conclusion through boring math. Second question. Do we allow electron to have minimal energy equals 0 in a box? Okay. Who would like to prohibit electron to have minimal energy equals 0? 1. Okay. Yeah. So, due to this confinement, like if the walls, if I'm claustrophobic, and the walls start like jamming me closer and closer, I will start panicking and running and trying to push it, and I will be very energetic because of the fear. So my energy will be definitely above 0. So same as with for electron. So how does energy of the lowest permitted state depends on the size of the box, on the length between the walls?
Inversely?
Yes. But this is the question, this is some scientific question that we can answer with long and boring math exercises. So Braden tells that it should be proportional, inversely proportional to the size of the box. But we will check him. Okay, so you have an idea what we are doing and where we are going, right? Any questions about the scientific challenges for this? Scientific challenges for this thing? No questions? Okay. So, have more visitors? Oh. So, this function will come up as the answer of our exercise. But if you're bored to follow it, you can just record it and then follow through. So it is very, very similar to what we did last time and what you were doing in previous week. It is solving boundary condition when function must be 0 at point 0 and function must be 0 at point L. And then we came with a solution that it will be sine function with discrete value of the rate. So it depends on x, but then this rate is proportional to angle, to integer number, and inversely proportional to the length. Okay. So you can call it wave vector, or it is related to the momentum. And then we just follow the one of the few equations that we need to memorize. Kinetic energy is momentum squared over 2 mass. And if we plug the momentum, we will get the value of energy. If I do it carefully, I am getting L squared, inverse of L squared. Either one of us is wrong. What? A minute ago, Brilliant told that the lowest energy of electron in the box is inversely proportional to the size of the box. I'm telling no, it is inversely proportional to the square of the size of the box. Well, from a common sense, from like a stranger from a street, it is not a big deal. But if you are going to quantitative science, or if you have major in math, it may be different functions, right? So, if you want to exercise your memory, it is something that you can try. It could be useful, or if you will teach similar course in your career, if you're looking for, even without teaching career, sometimes some of you go to industry and you do not care, but if you hate teaching but you go to graduate school for research, then you are assigned to be a teacher and you need to teach something. So, what do we see here? The integer number squared in numerator, the size of the box squared in the denominator, and then the Planck constant mass of electron in the denominator. What else? Which basically you will hear nothing new past this point. The rest will be technical details. So, how many solutions for eigenstate problem?
Infinitely many.
Yes, infinitely many. So we label them with index. Indexes. So solution number 1, solution number 2, solution number 3. And for the lowest energy, we put n equals 1. Lowest. So E0, we just plug n equals 1 and 2m I squared divided by L squared. Okay? So here is the answer to our scientific challenge. So there are strange traffic signs in the quantum world. They're not like do not drive quicker than 80 miles per hour. It tells like you're allowed to ride 10 miles per hour, 20 miles per hour, 30 miles per hour, but not in between. So discrete restrictions. And same for energies. The shape of the function. If n equals 1, just pi x over L, so it will be just one maximum, right? And it is kind of reasonable. Some probability to be in between. As far as we approach the walls, it will be less. So confined claustrophobic electron between the walls. And it cannot go through the walls if they are infinite. I don't know. If I have bad memory, then I split equation in parts and try to observe dependencies, but this is not a unique formula. You can see it in Wikipedia or in any textbook. So in modern world, there will be no situation when you need to memorize too much, because most of the time you have a Wi-Fi or whatever available. So benefits for community, benefits for society, for civilization, for engineers, and for technology. do you see any connections from these equations and from our scientific arguing between Braden and myself about this dependence on the lowest energy and the rest of the electronics, the light emitting flat panel displays? Laser pointers, CPU cores, and photovoltaic panels. How this 1/L² panel connects to civilization technology advances. Any ideas? You can develop ideas if you are shy to distribute it, or you can wait until I declare something. So here is the main idea of nanoscience and nanotechnology. Which I will tell in 1 minute. But before, most of you are chemists, and you do have a paradigm in your heads, which is not wrong. The paradigm that properties of materials are determined by their chemical composition. Right? So if you make the reaction, characterize that it is a single molecule, single type of molecules monodispersed in the solution, if you have a specific color, specific NMR spectrum, whatever, right? Wrong? Oh, not wrong. It is correct in most cases, but in the area of nanoscience, there are adjustments to these intuitive expectations.
So like gold and how it changes colors at the nanoscale?
Yes, yes. And gold, I remember you were prompting us to deal with metals several times. Metals are tricky. We will have tools to describe them, but it is much safer to deal with semiconductors. Mm-hmm. In gold, there are too many electrons, and semiconductors are easier, just to start with. So, by controlling size of the same material, including gold, but better take some, like, let's say, silicon, of which solar panels are made. You take same material, but you carve it on different size. And then suddenly it changes the color. You can go through the whole rainbow. How to etch? Well, it's not a problem for theoretical course. Although experimentally you can start nucleated, growing, and stop nucleation at some point, so it grows to a specific size. Or you can chemically etch by the strong acid to remove extra layers. But the main idea of nanoscience is that physical properties of a material are determined not only by chemical composition, but also by size and shape of the sample on the nanoscale. And this is most closely related to weight-Killing equation. Well, of course, we are not first who designed this equation, we just argued a little bit, but the energy of the lowest transition. So if you have a material, then color is defined by energy offset between like occupied and unoccupied molecular orbitals, right? This is not a surprise for you. And this is if we are talking about like materials, bulk, semiconductors, this HOMO to LUMO gap is a fundamental gap property of chemical composition. But if you start to shrink the material, the electrons there in these orbitals start filling the walls, and the energy of the gap increases. And actual formula is a little bit more complicated, but approximately it is whatever we have for infinitely large sample plus additional term that comes from the confinement. And if you take silicon, it's one step below the carbon. The fundamental gap is about 1 eV, and if you carve it in a size of like 20 angstrom, it will be in the. This one is infrared, it's black. But if you prepare samples of about a couple of nanometers, it will become yellowish. And if you tune it, if you make it smaller, it will be bluish. So you can tune the color. And through this, you can, this one uses different technology, but you can go to the Best Buy store and look for most expensive TV there. It will tell QD LED, right? If you saw it. So flat panels based on quantum dots. So you get different colors because of this effect. So what were we doing today in class? We were getting background for most expensive TV panels. Okay? So we can tell that it is a dream of chemical engineer or engineer in general. So get a material by request for construction or for electrical circuit or for optical properties. I need a material that emits at a given wavelength or that has so much energy offset to shut down the transistor. Or there are a lot of characteristics, and engineers who design devices or make constructions, they're shopping, going to Sigma Aldrich if it is chemical engineering, or looking through other catalogs of available materials to purchase, but not any property, not any material were available in the near past. But with advent of nanomaterials, one can design material of needed property by request. So what we do today is two boring equations, but they have strong implications for all civilization. Okay. If you're busy, if your schedule doesn't allow, I don't mind if you leave. But if you look through some math, we can go through together. So it is a couple of slides from last time. So we have walls and permitted region where the electron is moving. So you have Hamiltonian, same as for free particle inside and infinity outside. We were looking for solution in the simplest not mathematically, but simplest philosophical trial functions based on what we did before in the course. And at the very beginning, we spent a lot of time debating about that electron is a wave that can be traveling or standing. So we're just looking at superposition of two traveling waves traveling in opposite direction. And we just curious what are the momenta of these waves and what are expansion coefficients. So mathematical challenge, non-trivial challenge kind of stops here. After that, we just plug in this equation into where? I'm not going to give a surprise. So plug in a trial function into two words. Any suggestions?
Time-independent Schrödinger equation.
Generally correct, but we already know the Hamiltonian, we know the equation, and a little more narrow thinking, technical.
Boundary condition?
Yes. I was going to play like guess the letter. Okay. And here is just technical thing that nothing changes mathematically, and it is more exhaustive to our brains, but it goes. No, we try to make it easier for human brains. So if you replace the imaginary exponentials to near and dear sine and cosine, right? So two traveling waves with these coefficients, and then we combine cosines together and sines together, and then we can tell that this is new coefficient 1, new coefficient 2, or we can keep this sum and subtraction. And if we plug it into the boundary on the left, then the second term is 0, and for the first term, the trigonometric function is 1, which is possible only if this expansion coefficients for forward and backwards waves are opposite, equal in absolute value and opposite in sign. What do we do next? So we plugged it into the left boundary. Now we need to plug it into which boundary?
Right there, right.
Yeah, right. No. I need a grammar lesson. So, and before we go to the right boundary, we can, if we agree that C plus is minus C minus, we can replace C minus to minus C plus everywhere. And now we have only one unknown coefficient. So this imaginary unit comes as a heritage from Euler, right? The 2 comes because it was C plus minus C minus, but C minus is negative C plus. And then this KL is K is unknown wave vector. It is unknown for the next 10 seconds, times value of position at the right boundary. So we did the same exercise last time, right? Letters were a little bit different, but exercise was the same when we in your homework that you were grading. Remember? Problem number, I don't remember, 3? Yep. So last time we were not caring about, I was not caring about the normalization, and we just set up that sine can be 0 only if the argument is proportional to integer number of pi's, okay? Which gives us the condition for, what is it? It is quantum traffic sign. So only specific values of momentum are permitted. Well, for electron that is claustrophobically confined in a box. So it can move only with specific velocities and momentum. And now the most time-consuming and boring stuff is to find the normalization. Well, this is already what we did. If you plug in this permitted values of momentum into the free space energy, you get the set of energies that depend on discrete set of integers. I do not hear protest from professional mathematicians. Not integers. Probably one need to say natural numbers.
Yeah, that'd be more technically correct.
Yeah. So what is normalization? And where it comes from? It comes from the common sense that we have only, well, there are two interpretations of wave function. One, that it is probability of, it's not Tetris. Only Tetris is allowed in class. So one thing, one possible interpretation of wave function is that wave function square gives probability to find a particle, and another it is a particle density. But both probabilities gives us constraint. Total summation of probability density. Probability cannot be bigger than 100% on one hand, and on another one, even if it is density of electron, we have only one electron. So integrating over all space, we cannot get 2 or -1. So integration of this wave function square should be 1, right? So we take the function, we take its conjugate, with I becoming -I, and making sure that it will be equal 1, right? Well, we have still a little time.
10 minutes.
Super. So we have integration of sine squared of some argument. I don't know how comfortable are you to take integral of sine squared. I'm not. It's too hard for me. I prefer just take integrals of linear argument, like sine of something. But we do have 3 trigonometric relations, right? So this doesn't surprise me. Okay. If it would, we could derive it, but maybe we skip this pleasure for other time. So replacing sine squared to 1 minus cosine of double argument, and then we need to divide everything by 2. Right? So 1 minus cosine of double argument. Make sense? And then we are integrating double cosine. And you know, sometimes you can save time when solving all these problems graphically. You just draw the function, so cosine. So if it will be cosine of single argument, it would make probably this shape. But if you have double argument, it will do it will oscillate moving in. But we integrate from 0 to L, and integral is area under the curve. So if you add together this plus regions and minus regions, even if you've forgotten how to take integral cosine, you can intuitively see that it will be 0, right? And then we have only integration of dx from 0 to L, which will give us L, right? And this all should be equals to 1. Yeah, one can carefully take this integration, but it will be 0 for the second term. And by solving it for the C coefficient, one can get the normalization factor 1 over square root of length. So if So we are getting 1 square root of x sine e and x divided by m. Any objections, any questions? Are you happy or against skimming through derivations? Would you prefer me having blank pages and divide it slowly step by step? Well, you can develop your opinions and share in private. If I would be sitting in class, I would hate this style because it is too quick and it is not possible to follow. The instructor can lie and just compensate lie by quick flashing through the slides. Doing slowly maybe is more time consuming, but then one can prove any step and debate it. So I think we are done for today. No, please do not applaud. Any questions? I think we are earlier by 4 minutes. So it is, I'm returning you minutes that I was borrowing before. So looking forward to see you, well, those of you who are enthusiastic about homework, 5 p.m. QBB 132.